All right, everyone, we have two types of projectile motion questions at this point. Two types. The first type is when we launch an object horizontally off the edge of a building or of a cliff or something like that. The second type is when we launch an object at an angle from ground level and it ends up at ground level. Let's make the angle here 30 degrees. Let's make the speed 10 meters per second. Let's make this speed 10 meters per second. Let's make the initial height 15 meters. So how do we go about analyzing both of these problems? Well, we start off in exactly the same way. We have x, we have y. For x, we say delta d is equal to v is equal to delta d over delta t. And for the y component, we say that delta d is equal to vit plus 1/2 at squared. Nothing new there. I told you question number one on your final exam is going to be one of these two questions, and you're going to have to write down these two equations first off before you do anything else. Doesn't matter whether it's problem number one or problem number two. They both start off exactly the same way. Now, before we go any further with this one, we probably want to get rid of that funny angle, right? Because we don't like the funny angles. So we go off to the side here. We get 30 degrees. 10 meters per second, x component, y component. When you do some trigonometry on this, x ends up being equal to 8.66 meters per second, and the y ends up being equal to 5.0 meters per second, right? Cosine 30 degrees, sine 30 degrees, 8.66, and 5.0 meters per second. So far, other than resolving that angle, they're both exactly the same question so far. Let's point out some differences now, though. The first difference is v, the x velocity. The x velocity in the first problem here is 10 meters per second. It's the number that we're given for the x velocity. We don't have to do any calculation with that. It's just you got the number 10 meters per second, plug it in. For this one, you got to do something with it. You got to resolve it into components. It's not 10 meters per second. In this one, it would be the 8.66, right? It would be the x component of the initial velocity. So the first difference between these two problems is the x velocity. First one, it's just a number that's given to you. The second one, it's you got to find it based on the number that's given to you along with the angle. Second difference, delta d. Delta d in the first problem, for the y component that is, delta d is what? Tell me what the value of delta d is, Seth, for the y component in the first problem over here. Almost 15 meters, you're really, really close. Yep, negative 15 meters, right, Seth? Because it ends up below where it started, right? Tell me what the y component of the displacement is for the second problem. A change in position, where it lands relative to where it starts. Jordan? 0. So there's the second difference. Delta d for the y component. Now, delta d for the x component is going to be different as well. It's going to be a different number as well, but it's not a difference in the way that we think about the question, right? We solve for delta d for the x component. It is what it is. Different values, but we do it the same way. We think of the x velocity differently for these two problems. We think of the y displacement differently for these two problems. The final difference? The final difference would be vi for the y component. Vi for the y component in the first problem is what, Kevin? How much of the 10 meters per second is on the y-axis? None. So it's going to be 0. Vi for the y component is going to be what? 5 meters per second. So it's whatever the y component of the 10 meters per second was. So the third and final difference. Now at this point, it's just a matter of plugging in your numbers, solving for whatever it is that you're looking to solve for. Does that make sense? If you understand what we've just gone over, okay, you should be able to solve the problems that were on your worksheet, but you should also be able to solve the problems that will appear in your unit test on Thursday, and also question number 1 of your final exam that's going to appear at the end of January. All right, we had some homework questions based on your worksheet. Worksheet number 10. Worksheet number 10, I think we had questions 4 and 5. The answer number 4 was 38 meters. And the answer number 5 was 56 meters. And then worksheet number 11, I believe in worksheet number 11, all we had was question number 4. Is that correct? They didn't assign question number 5, correct? Number 4, the answer worked out to be 70 meters per second. All right, is there any of those questions, 4, 5, or 4, that you'd like to go over here now? Ryan? This one? Okay. Any others? Just that one? Okay, that's not bad. Not bad at all. Worksheet number 11, question number 4. The question says a cannon fires a cannonball 500 meters downrange when it's set at an angle of 45 degrees. So it looks something like this. Right? The cannon's firing it at 45 degrees, which, by the way, if you want to maximize distance, the range, sometimes we call it, the optimum angle is 45 degrees. If you go below 45 degrees, the height isn't enough to give you enough hang time to get enough distance. If you go above 45 degrees, the hang time is greater, okay? But you don't have enough x component of velocity to have it downrange, to have it land downrange. So the optimum angle, if you want to maximize the distance that it travels, would be 45 degrees. That's in a mechanical system. Biologically, if you were throwing a ball, which you're actually going to do here in a few minutes with the activity that we're going to do, if you're throwing a ball, the optimum angle is actually more like 38 degrees. Even though the physical optimum angle is 45, biologically, okay, anatomically, your shoulder doesn't like to throw at 45 degrees. So it actually becomes a little bit less efficient to throw it at 45 degrees just because your body's not designed that way. It's not designed to throw it at 45 degrees. Okay, again, but physically, 45 degrees is that optimum angle. It ends up 500 meters downrange. And we're looking for the velocity, or really the speed, because we already have the angle, right? The speed at which it's launched. Okay, tricky question here, tricky question. But somewhat like the activity that we're going to do today. Not exactly, but somewhat like the activity we're going to do today. Okay, we know what to do here. We break it up in x and y components. Nobody should say, I don't know where to start here. Okay, every single question involving projectile motion, you should start off with v equals d over t, and d is equal to vit plus 1/2 at squared. Every single one. So nobody should have a page in front of them that doesn't have that written down. Everybody should have that written down. Even if you didn't know where to go with it from there, everybody should have that at least. Okay, v. Don't know what that is, do we? It's something at 45 degrees, but we don't know what it is. Delta d for the x component is 500 meters. Delta t, we don't know. So that wasn't very helpful. That often happens to us, right? We often go through one of the components, and it isn't very helpful to me. So let's go to the second one now. dy. Bart, what's delta d for the y component there as this ball is launched from the ground and ends on the ground? Nope, for the y component. 500 meters was the displacement for the x component. Where does it land vertically relative to where it started, Tyler? Good, 0. That makes sense, Bart? 500 meters downrange, that's the x displacement, not the y displacement. Assuming it lands on the same level as it started, then our y displacement will be 0. vi, don't know what that is. Delta t, don't know what that is. A is neg 9.81. Delta t squared. Oh boy. This doesn't look pretty. Here's what we can do, though. We can cancel out a delta t, just like we have with the other problems involving a projectile launched at an angle. 0 divided by t is 0. VIT divided by t is VI. So in fact, 4.905, that's a half of 9.81. T squared divided by t is t. All right, a little bit simpler, but we still have two unknowns in that equation. So how are we going to deal with this? Anybody get the answer, by the way? How did you get it? Oh, I thought your hand was kind of up there. Nobody? Okay. So what are we going to do? Well, remember, this is Vx, right? This is VI y component. I'm going to put those subscripts in there, even though I don't usually do that. I'm going to put them in there because I need you to see that they're different numbers right now. Vx, if we were able to resolve that, Carolyn, you got something for me there? Yes, you're going to ultimately do that, but be careful. Vx and Vy are two different numbers right now, so you can't do that quite yet, but you will soon. This is going to be Vx, and this is going to be Vi y. This is just V. If we do some trigonometry, we would find that Vx is V cosine 45 degrees, right? Cosine 45 is equal to adjacent over hypotenuse. Rearrange it. Vx is equal to V cosine 45. So let's replace that. V cosine 45 degrees is equal to 500 over t. It's not Vx anymore. It's just V, V being the hypotenuse. So I'm going to put that in another color, actually, just to drive that point home. Okay, we don't look like it doesn't look to be any closer to being done, but we are actually a little bit closer here. For the y component, we're going to say 0 is equal to, what's VIY? Well, if we were to say sine 45 is equal to opposite of the hypotenuse here, and rearrange that, VIY would be equal to V sine 45 degrees. V being the hypotenuse, V sine 45 degrees, subtract 4.905 times t. Now we have two equations, both with two unknowns, but this time it's the same two unknowns. Instead of being Vx and t, Vy and t, now it's just V and t. Let's simplify it a little bit. Cosine 45 is 0.707. Let's take this to the other side. 4.905 t equals 0.707 times V. Make sense? So far, so good? It's a hard question, guys. Any way you look at it, it's a hard question. But does the logic make sense here? Not asking, could you do this yourself tomorrow? But does the logic of what I'm doing make sense so far? Hey, look at that. 0.707V, 0.707V. If 0.707V is equal to 500 over t, and it's also equal to 4.905 t, then let's set them equal to each other. Let's say 500 over t is equal to 4.905 times t. See what I've done there? If these two numbers are exactly the same, then these two numbers have to be exactly the same as well. Now I can rearrange this to solve for t. 500 is equal to 4.905. This t goes up by multiplying times t squared. Now let's do this on the calculator. Let's say 500 divided by 4.905. Let's square root that. We end up with a time of 10.096 seconds. Okay, there's my time. There's my time. Now I want to find V. Put it into either of these equations. let's take the cos 45 down by dividing. So let's say 500 divided by bracket 10.096 times 0.707, which is cos 45, gives me 70 meters. Wow. Boy, I sure hope you don't get one of those on the test, eh? How many people feel like they could actually do that if they did get on a test? Okay, well, one of you, two of you. It's a hard question. Nobody got that, eh? That's okay. Honestly, guys, I expected you guys to have a tough time with that question. That's okay. It's good mental exercise to struggle with a question sometimes. Okay? We don't always want to have immediate success. Okay? We want to exercise our brains a little bit. And that's exactly what we've just done here, is exercised our brain. Now, the good news is, I said the activity that we're going to do today is a little bit like this, in that we're solving for V, but it's going to be much easier to solve for V because of one of the variables that we're measuring. Okay, we're going to measure the time in today's activity, whereas in this one, in this question, you had to solve for the time right here. And that was the toughest part of it, right, is recognizing that you had to set this equal to this to get the time. You're going to have the time today. So it becomes quite a bit easier to solve this problem. Here's what the activity is going to involve today. And this is not a write-up. This is not a lab, not something to be marked. It's just something that we're all going to do ourselves as just a little bit of an exercise in projectile motion calculations. Each one of us is going to go outside. We're going to have class outside today for at least a little while. We're going to go outside and we're going to throw a ball. Now, please do not throw the ball as hard as you can without warming up. If you're not a baseball player or a football player and you're not used to throwing a ball, you could hurt your shoulder if you just throw it as hard as you possibly can right off the top. It's not a competition to see who can throw it the farthest. Okay? If you play baseball or softball or football or whatever, and you go through your normal warm-up routine before you throw it, then give it a throw. Okay, but if you don't normally do that, then don't throw it as hard as you can. Just even a soft little toss is fine. Doesn't matter. Got that? I don't want anybody to hurt themselves here. So everyone's going to throw it. You're going to throw it with a certain speed, but we're not going to know what that speed is. It's just speed, whatever. Okay? You're also not going to know what angle you're throwing it at. In fact, that's what you're going to try to find, is the speed that you throw it at and the angle that you throw it at. The ball is going to follow a parabolic path. It's going to follow a parabola, as we've said a million times here. And it's going to land downfield somewhere. You're going to measure two things. You're going to measure this distance right here. We're going to call that delta D. Usually I don't put the subscript there, but I am this time. Okay, delta D x, you're going to measure. And you're also going to measure the time. That's it. Measure how far it goes, and you're going to measure the time. Now, you're going to need to work with people here. We've got 5 softballs up here. We're going to break it down into groups of 4 or 5. Okay? Doesn't matter if it's with your buddies. It doesn't matter if it's your normal lab partners. It doesn't matter. There's no write-up to do here. We're going to come back after everybody's got their numbers here. Okay, we're going to come back. We're going to crunch our numbers to see what the initial velocity that you threw with. And that's it. It's just going to be a little paper and pen exercise after we collect our data. So it doesn't matter who you're with. You don't have to be with the brilliant person who can help you out with the lab. It's not a marked thing, okay? Doesn't matter who we're with. You could go by rows just as easily. So how are we going to determine that, though? How are we going to find out what your velocity is? This stuff right here, what you're trying to find. Well, where should we start? Mathematically, where should we start? I got 23 people in this room right now. All 23 of you should know where to start. Where are you going to start? Yep. Write down your equations, right? We know we're going to use those equations. We might be at a loss as to what we're going to do with those equations, but we all know where to start. V is equal to delta D over delta T. And of course, for the Y component, we're going to say D is equal to VIT plus 1/2 AT squared. V, we don't know. This is the x velocity, right? We don't know what its value is. The displacement, we will know. Right? We're going to measure that. No, I don't know what it is right now, but we will know it. The time, we'll know that as well because you're going to measure that. That's going to give you V, the x velocity, whatever number that happens to be. Now you're going to go over to the y component, delta D. We're going to make an assumption here that isn't quite true, but it's going to work for us. Pretty close. We're going to assume that the ball lands at the same level as it was thrown from. The reality is when you throw it, you're throwing it from about 1.5 meters in the air, right? And it lands 1.5 meters below where it started. Why do I not want to use a displacement of negative 1.5 meters or so? Yeah, then we'd have to use the quadratic equation to solve for t, and not all of you are familiar with the quadratic equation. So we're going to make that assumption, that simplification, that isn't perfect, but it's close enough for the purposes that we're trying to accomplish today. And delta D is equal to 0. VI, we don't know. Delta T, we're going to measure. Delta T again, we're going to measure. So you're going to solve for Vx in the first equation. You're going to solve for Vi. Remember, that's the y component in the second equation. Once you have Vx, once you have Vy, you can solve for V using the Pythagorean theorem, and you can solve for theta using the inverse tan function. Now, it's not a competition. It really isn't. But we can compare one person's numbers to another person's numbers, okay, even if we're not trying to beat the next person. Let's say that Zane throws the ball 40 meters. Okay, let's say that Zach throws the ball 37 meters. Does that mean necessarily that Zane threw the ball harder than Zach? Because he threw it farther? No, we'll see. When you calculate the speed, is it possible that we would find that Zach's speed was actually greater than Zane's, even though the ball didn't go as far? Sure it is. Depends on the angle, right? If the closer to 45 degrees you are, the more you're going to maximize that distance, right? So if Zane threw it at close to that angle, but Zach threw it at 12 degrees, well, maybe he still threw it harder. It just didn't go as far because his technique wasn't very good, right? He wasn't throwing it at a good angle. Make sense? So any questions about that?